today try to finish off chapter 5 and then go on to chapter 6. Okay, chapter 5 was the rational function, polynomial function part. And chapter 6 will be exponentials and logarithms. Okay, so today I wanted to wrap it up by doing an old quiz. So I posted these on Power Campus. And so if you check that, I've actually posted all the quizzes there. And so you'll see the ones we've already done, chapter 3 quiz of last semester. These are all the ones for last semester. And so you'll see the next one as well, the one on polynomials and rational functions. Okay, so I'll go through those questions today, finish it off, and then start on the exponentials and logarithms. First, let me check a couple of things here. I'm just going to check the broadcast. Oops. So I'll just check it. Okay, seems to be working. Okay. All right. Now, okay, so last time I was looking at the following rational function, and I just want to make a note of this particular rational function. Remember last time in the lecture I simply guessed that it might have this appearance here. Okay, so in other words here the graph will come down like this and go up like this, and it will go down first and then up here, then here it will go up first and then down here. And I guessed that the maximum was going to be at x equals 0. And yeah, so, and that's actually what it turns out to be. The maximum is here, the local maximum I should say, is indeed at x equals 0. It's not a global maximum because there's a part of the function up here which is greater than, the y values are greater than the y value here. But this is a local maximum. So it's a part where the function goes up and then goes down. So in this region here, it is a maximum. Okay, so the way you can see that right away is that the numerator here has the form x squared, and the denominator is the form x minus 2. So in the vicinity of x equals 0, the numerator looks like x squared. So this is a similar, this is an idea that was similar to the one for simple polynomial functions. So after you factor simple polynomial function, and you want to look at the behavior near roots, remember you look at each factor, and if it's polynomial, then if it's a power law. If it's a power of that factor, then the polynomial has a simple power law. It looks like the power law behavior near that root. And then you take the rest of the factors, which are not 0 near that root, right? And then you would simply plug in the value for the root that you're looking at. Here it's x equals 0. Okay, so the other factors for the polynomial will say be x minus 2, x minus 3, and you have an x squared here. So you just look at those factors, and if that factor turns out to be positive, then the polynomial is touching from above. If that factor is negative, then the curve looks like this. It's touching from below. So that's exactly what happens here as well. If you plug in x equals 0, then you get this factor minus 2 in the denominator. So that just means that it's opening downward like this. so near the root, also of a rational, it works for rational polynomials in a similar way. Near the root of the numerator, you look at the power law behavior of that factor that's contributing to that root in the numerator. And all the other factors, whether they be in the numerator or denominator, you just evaluate at that root, and then it gives you, in this case, a negative sign, and that shows you that it's going to be just touching from below. So it has an even power. It's just going to be touching the graph. So that's why you can actually look at this and just guess that this is going to be the behavior. Okay, I did it a different way as well. But that's just going back to this whole thing. Okay, so in that, just to review what we did last time, we looked at rational functions. We looked at the different kinds of asymptotes that you can have, whether they be horizontal, vertical, or slant asymptotes. Okay, we saw this had a slant asymptote of y equals x plus 2. And actually this function here is obtained from this other one by shifting. So the other one that we did, it's called a g of x plus 1 over x, right? That had the form where you had the asymptote y equals x, and this graph approached that and had an appearance like this, had a behavior like this. This point here actually turns out to be 1 and 2. And this turns out to be minus 1, and at 2, sorry, minus 2, you have this point where it turns around here. So this is what it looks like. And now, how do you know? One time last semester, a student asked me, is there a simple way of verifying that this has a minimum here and a maximum here? The minimum value is at x equals 1, and the actual minimum value. Okay, the location of the minimum is at x equals it's a local minimum at x equals 1, right? You can locate the minimum simply by specifying x, since y is automatically determined, right? Because it's a function. Okay, so local minimum is at x equals 1, and the value of the minimum, namely y is equal to 2 there. All right, so how can you tell? Okay, how do you know that that's the minimum? So a student asked that, and I showed him that there's a trick here. And the same thing will work for showing that there's a local maximum at x equals minus 1, namely minus 2. So first of all, you can get one from the other by symmetry. Okay, so here's the trick. You show that this can be written as it's like you complete the square, with a minus sign between the two terms. So this is not quite the same thing as the way you complete the square earlier. Here you take this, you take the square root of this one and the square root of this one. So you take the square root of x and then minus the square root of 1 over x. All right? So I claim this is going to be, to get the middle term, I'm going to have to, you can see if you multiply this term by this term, you're going to square this. You're going to get this times 2, which is going to cancel the x, the square root of x in each factor. Also, for this to work, x has to be positive. So I'm in this region here. X is positive here. So this is the graph x positive. So I'm just looking at this part of the curve. All right, so for x positive, I can simply take the square root of x, put that in here, square root of 1 over x, put it in here, and then if I square that, I'm going to be different from this by just a constant. What is that constant? Well, here if I multiply this out, I get let's multiply it out. I get x back, right? Here I get 1 over x back, and here I get minus 2 plus the rest. Okay, minus 2 is it's because this times this is minus 1, and then I have to multiply that product by 2. So I get minus 2. And now, so therefore I have to add 2 to keep this side equal to this. Okay, so I write it like this. Now what's the use of doing that? Okay, well now I've shown, since this is a number squared, this part is always positive, or 0. So I can say that this is greater or equal to 2. And furthermore, when is this equal to 0? This will actually be equal to 0. So it's not just that it's, you know, if it's never equal to 0, then I really should say it's greater than 2, strictly greater than 2. But I'm allowing the equality because there is one value of x for which this whole thing is 0. That's the only way I could get equality here. So equality when this is equal to this. When does that happen? Okay, so square root of x minus 1 over square root of x. So equality when this is equal to this. So you just solve for x, you just put the square root over here, and then you just, the square of that is simply x, and that's equal to 1. Okay, so I just shown that this function is always bigger than or equal to 2 along this part of the curve. And furthermore, it's exactly equal to 2. So equality when x equals 1. Okay, so that's where the minimum actually is reached. Okay, so that's my math trick of the day, just to show how it's positive, or how this part is a local minimum at x equals 1, and that the minimum value is 2. So for this function, going back to this function, okay, I remember when I did synthetic division, this became x, and then I had plus 2, and then plus 4, right? Over x minus 2. Yeah, because when I did synthetic division, I got 1, 0, 0. I put in my 2, and I got 1 times 2 plus 0 is 2 times 2 is 4 plus 0 is 4. So the remaining polynomial is x plus 2. The remainder is 4. Quotient polynomial is x plus 2. Okay, so this whole thing looks very much like this other function, except we have instead of x, we have x minus 2 in the denominator here. And we have a 4 up here. Okay. So if I replace my variable, let's try u as a variable. So u gets replaced by x minus 2. I just replace x minus 2 everywhere by u. So therefore x is equal to u plus 2. When I substitute that back into the equation, I get a new function capital F of u, which is u plus 2 plus 4 over u. So it's u plus 4 over u plus 4. Okay, so this function is very similar to this one. It's got it's just it's not quite the same, but anyway, you can. What I've done is I've shifted the whole graph so that at u equals 0 now the graph has an asymptote. Right? Instead of x equals 2 as I had before, there's a vertical asymptote, but here it's at at u equals 2. U equals 0, sorry. All right. And it's also been shifted up by 4 from where it would look like this other graph, which I just erased. Okay, so if I take the new variable v to be y plus 4, sorry, y minus 4 is what I want. Yeah, so this right now is y as it stands. So now I want to take the 4 put on this side and call it v. All right, so if I take this new variable, so I basically I'm shifting down by 4 and calling that new variable v. Then this equation says v is equal to u plus 4 over u. And this, from the method I showed you just before, this, when I complete the square, will be u minus 2 over root u squared, and then I'll get a 4 here. Actually, that was already in the form of the perfect square that I wanted, so plus 4 oh no, sorry, it wasn't. It was, yeah, I had the wrong sign here, actually. So I want a minus sign in there. And so, anyway, this is equal to this. And this is bigger than or equal to 4. when u, this is for u positive. So again, I'm looking at the graph will look like this. I'm looking at the part where u is positive. So I'm looking at this part here. The slant asymptote will be same as before. Oh, sorry. Yeah, it will be the same as before. V equals u. All right, and the maximum will be at u equals 2 now, because this is equal to 0. This whole thing is equal to 0 when u is equal to 2. So you just solve for that. 1, 2, and then this will be up at the maximum value will be 4, or the minimum value will be 4. 1, 2, 3, 4. So here's what it looks like, and the graph comes down and then starts going up again like this. All right. And then there'll be a similar part over here. 1, 2, 3, 4. 1, 2. So this will come up and go down like this. These are asymptotes here. All right. -2 and -4. So these are the 2 points. 2, 4, local minimum. Here is -2, -4, local maximum. Okay, so now the original, this is, how did I get this graph? I shifted x to the right by 2. Let's see. No, correction. In order to get u, so I transformed to this new variable u. I added, so I replaced x by u plus 2. So that takes all the, let's see. Yeah, any value of x before, to get u, I subtract 2 from it, and I get the new variable u. So actually what that means is I'm shifting to the left. So this is the graph, right? Because the previous minimum was at 0, 0. It was sitting up here. So I have to shift this new minimum, or this new maximum down here, to the left first, and then shift down by 4. So when I take each x value and I have to decrease them by 2, those give me always the new value. Instead of x, I call it u now. It gives me the new value for the new variable u. And similarly up here, I take all my y values and I subtract 4, so that'll shift the whole graph down. So that's how come this got shifted over here, and this is down there. And likewise, this was over up at x equals 4 and y equals 8. So the local minimum was in the old graph. It was at x equals 4, y equals 8 in the old graph, and the local max here right, is at x equals 0 and y equals 0 in the old graph. Okay. All right. So the way you could see that in the end is you can write back in terms of the old y and x values. So this is x minus 2. This is plus 4 over x minus 2. All right, so the graph that I showed was obtained from this one. Actually, you would start with this one. You would start with this one, and this one would tell you so this part says you start with this graph and then you shift to the right by 2 horizontally, right? Because you're replacing the value u by x minus 2. So use like the old x. So you replace x by x minus 2. And then you shift upward. So you take this graph to get the correct graph in terms of x and y. You shift to the right by 2 and then up by 4, which is what this means. Okay. And so you get a graph which looks very similar to what I had before for the first example. But it's shifted in 2 ways. Now that brings up another thing. Symmetry, so there is a symmetry here, even though this is not, as I wrote down here, this is not an odd function or even function. So it doesn't have a direct symmetry. If you replace x by minus x, then you don't get a change of y, or you don't keep y the same. So it's neither even, so it's neither odd, which would be the first case if y change the sign, nor is it even. Okay, so, but it is odd if you go to these variables. Okay, so I've shifted it horizontally and vertically, and then it's odd with respect to that choice of origin. So you can have a symmetry with respect to a vertical axis, which is not the y-axis. So it's like an even symmetry. So you might have a function which is an even function shifted over. Okay, so this has an even symmetry with respect to an axis different from the y-axis, with respect to some line here, some vertical line. In this case, x equals a. I should say with respect to. Or you could have a function like this. This is odd with respect to the point. In this case, it'll be 2, 4, because that's what this graph looks like after I shift it back. Okay. So the actual x and y axes will be over here. So this is odd with respect to, so this point will be 4 and 8. X equals 4, y equals 8. Actually, sorry, that's not quite right. 2, it's with respect to the point. This point here is the point of symmetry. 2 and 4. Okay. All right, so that's just a word about that graph which comes up. Sometimes you have symmetry, but it's not always obvious. Okay. You might have symmetry with respect to another line somewhere else other than the x-axis, or other than the y-axis, I should say. Okay. Now let's do these problems that I gave for last semester for the quiz 2. Have them up here. So the first one is find the quotient and remainder obtained by dividing x cubed minus 2x, sorry, plus 2x minus 5. Let me check that. Yeah, x cubed plus 2x minus 5 by x plus 3. Find the quotient and remainder. Use any method. Okay. Find the quotient and remainder obtained by finding x cubed plus 2x minus 5 by x plus 3. Okay, so the simplest way might be using synthetic division. So I'll just do it that way. But you could also use long division. Okay, so the coefficients are 1, and I have to skip 1 here because there's a 0. Put the 0 in. 2 minus 5. Okay. And I put in, evaluate this at x equals minus 3. And this will give me the coefficients of the quotient and the remainder, all in one operation. So minus 3 times 1 is minus 3, add 0, minus 3. Times itself, 3 minus 3 times itself is plus 9, plus 2 is 11. Finally, minus 33, and I get minus 5, minus 38. All right, so we can also check that by plugging in. You should get the remainder, but that's just by evaluating this at x equals minus 3. And checking that, we get minus 27. Plus 2 times minus 6 and minus 5. So that's 27 minus 11 is minus 38, so that checks. Okay, so this is our remainder. So we get x squared minus 3x plus 11. And remainder is minus 38. All right, so yeah, if you have any questions on these solutions, please write me an email, or let's see if I can, oh, you can't play the video. Okay, so somebody did already chat here. Okay, so I'll try to somebody says they couldn't couldn't play the video. Okay, so I would try again later if you can't hear it or see it. So it does seem to be working at my end. It does seem to be live, and the stream health does seem to be fine right now. Okay. Another thing you might check is to try to make it go live. Sometimes it will wait, and you have to click and make it go. Slide the slider all the way to the front, and maybe that will make it go live. So it'll just be delayed slightly then. Okay, so next problem. Let's just see if I can so I just typed it in the answer for him. Okay, so let's go to the next question. Which is, use synthetic division to find the quotient and remainder obtained by dividing x to the fifth minus x cubed plus x squared minus x plus 1 by x minus 1. So here we are required to, that was number 1, this is number 2. So this one we are required to use synthetic division, which I probably would have used anyway. So x to the fifth minus x cubed plus x squared minus x plus 1. We want to divide it by x minus 1. Okay, so again, you write down the coefficients. This is x to the fifth, this is x squared, minus 1, plus 1, minus 1, and plus 1. And then we simply evaluate at x equals 1, so that's a 1 there. Okay, so I start my evaluation, and I get 1. 1 times 1 is 1, plus 0 is 1. Times 1 is 1, minus 1 is 0. Times 1 is 0, plus 1 is 1. Times 1 is 1, minus 1 is 0. 0 plus 1. Okay, so you just get the 1s and 0s here. The remainder is 1. And the quotient polynomial is, so here I have to remember this is x to the fourth now. So it starts off at x to the fourth plus x cubed. And then I get plus x. There are zeros elsewhere there. So then, I think I was asked to check this as well. Okay, so we're asked to check this answer. Yep, so we take our quotient and we multiply by x minus 1, and then we add back in the remainder, and do we get the original polynomial? And so I just multiply it out, and I get x to the fifth plus x to the fourth plus x squared, and I get here minus x to the fourth minus x cubed minus x, and then add 1. So here we have the x fourths cancel, and everything else Looks like we just leave it the way it is. And we can check every term is there. So x to the fifth minus x cubed, the order has changed here a little bit, plus x squared minus x plus 1. So that is correct. It's equal to the original polynomial. Okay, I'm just going to check that the first part was... Okay, I guess you were asked also to check the answer for the first part. Okay, so what was it? X. This was, sorry, this was 1b. So let's check 1a. Okay, I forget what it was, but let's see, x squared is minus 3x, and plus 11. And the remainder was minus 38. So I just want to check this. This whole product is equal to the original polynomial that I start with in the numerator. So x cubed plus 3x minus 3x, sorry, plus 3x squared minus 3x squared, that cancels. Then I get minus 9x plus 11x. And here I get plus 33. And I get minus 38. So these give me, this combined to give me 2x. And this combined to give me minus 5. And that looks like it's correct, yes. That's what I had started with. Okay, so it's important to know how to check. In fact, I'm asking you to do it on quizzes. So please be prepared to be able to do that if necessary. But in any case, do it, and that will help to verify your answers properly. Okay. So it's just a good habit to be in, whether you're asked to do it or not. Okay, so let's go to the next one. Okay, so this was actually the final, this was kind of a bit of a shorter quiz, but anyway, the final question was to graph a rational function. So it was y equals x minus 2 over x squared minus 1. This was question 2. Show clearly, it says, any A asymptotes, B zeros. So C intercepts and D verify the graph by finding at least 2 extra points on the graph which are not zeros or intercepts. Which are not zeros or intercepts. Okay. So the first thing to do here is to factor both numerator and denominator, and we do so, and so this is the difference of squares, so it's the sum of the difference. Okay, so x minus 2 divided by x plus 1 times x minus 1. All right, so now, what does this all mean? Okay, so So to find the x-intercepts, you look at the zeros of the numerator, right? And to find the y-intercept, you put in x equals 0. All right, so first the x-intercept, there's 1 here, at x equals 0, and then y is equal to 2. The y-intercept, you plug in x equals 0. So the function at x equals 0 is, this becomes 0 and I get minus 2, y is equal to minus 2 over minus 1, which is simply 2. So that's the y-intercept, 0, 2. The asymptotes are obtained by making the denominator equal to 0. By the way, these are also, this is a 0. So that's class requirement to find all the zeros as well. The A is asymptotes are at x equals 1 and x equals minus 1. And then D, find at least 2 extra points. Okay, so better not one of these. Okay, so let's try. We can use a table, and we could try evaluating x equals 2. Is 1 point. Neither of these will. Oh, actually, it's an intercept, right? Sorry. So 3. X equals 3 gives us 1 over 3 squared, which is 9. Minus 1 is 8. And then possibly 4. We should be, it's better to give a range of values here, so not all on the same side, in other words, of the x-axis, of the y-axis. So here, if I plug in 4, you get 4 squared minus 1 is 15, and you get 2 over 15. Oh, also the asymptote, we want to find, these are the vertical asymptotes. What is a horizontal asymptote? Okay, well now you can see the degree of the numerator is 1 less than the degree of the denominator, so if you take x larger and larger, then the value of y will become 0. So it's just y equals 0. That's the only horizontal asymptote. You can see these values will get smaller and smaller as x becomes bigger and bigger. On the other side, at x equals minus, let's say, 2. For a little bit of variety here, I'll take another point. And I get 2 squared, again, that's 4, minus 1 is 3. This I get minus 4 over 3. Okay, and you could possibly take other points to see what it is, what it's doing elsewhere. Now, another, to make graphs, to make the graphing go a little bit easier, a useful thing to do is to check right away. You can check what the sign of y is in these intervals here. So these factors represent these factors have the points associated with them. The point is where this factor will change sign. So this factor is associated with the point 2. So along the x-axis, if I put all these points, minus 1, 1, and 2, it's 0. Okay, so these factors will change sign. Let's draw sort of a picture of showing what signs each factor has along these intervals. So if I just write the factor over here, I'll start with the lowest, the smallest root or the small zero of one of these factors, it's -1. And then I'll look at the next one, which is 1, and I'll look at the final one, which is 2. Okay, so this factor is negative over here, to the left of -1. So I'll just put a minus sign here. Okay, so there are the 4 regions actually, where this could change sign, and we could have different signs. Now this factor by itself will only be negative on this side, and will be positive in each of the other 3 regions. Okay. Right now it doesn't matter whether the factor is in the numerator or in the denominator. For these factors, I won't consider these points anyway. These are out. These will be asymptotes. But you can still change the sign going from one region to the other. And the sign doesn't matter whether it's in the numerator or denominator. It doesn't make a difference as to the sign of the factor. So here, this factor changes sign when I go past 1. So it will be negative before 1 and positive after 1. And finally, this factor changes sign only if I pass through 2. So it'll be negative before 2 and positive after 2. Okay, so these are my signs of the 3 factors. Altogether, when I take the product and quotient like that, the entire rational function will have a negative sign on this side, this interval. Here I'll have a positive sign. One factor has changed. Here you have only a negative sign. Again, one factor has changed sign. And here I'll get a plus sign. So we'll alternate being positive, negative, positive, negative, positive on each of these 4 regions, 4 intervals. Okay, so let's see what that looks like on the graph. Okay, so my asymptotes are at x equals, vertical asymptotes are at x equals -1. So I'll just write one in here like this. +1, show another one here. And at x equals 2, I'll have an x-intercept. So the graph will go through the x-axis at that point. And by the way, what is the value of the factor, or the instantaneous slope as I go through that point? You just take the other factors and evaluate those at x equals 1/2. So that's going to be 1 over, or x equals 2. 1 over 1 plus 2 is 3, and this is going to be 1. So it's going to be 1/3. So it's kind of a gentle slope going through that point like that. It's going to be positive as well. Now, okay, so putting all these things together, over here the graph is negative. Okay, furthermore, there's no passing through the x-axis here. There's no 0 there. And it's approaching this asymptote, which is the horizontal asymptote, which is the x-axis. Okay, so that's going to be negative, so it's below 0. So it's approaching, if you go in that direction, it approaches -infinity it approaches 0 from below. So it'll look like this. And I evaluated -2, and that is indeed -4/3. So at some point over here, it's -4/3, which would be here. Then it approaches this asymptote like that. Okay, put arrows there. Okay, so this should be a smooth thing. There. And I'll label that point, -2, -4/3. Now, it switches sign, so that means when I go through -1, the graph will come down from +infinity, so it'll come down from here, and then it actually won't cross the x-axis because there's no zeros in here. So it'll actually go keep positive all the way through this interval, and we'll have to go to plus infinity at x equals 1. Okay, so somewhere around here is a local minimum. Okay, I'm just roughly drawing the sketch. It doesn't necessarily have to be when the near the y-intercept. The y-intercept, by the way, that should be 2, so that's right here, 0 and 2. Okay, and then on the other side, it becomes negative between 1 and 2. So here's 2. So again, it comes from minus infinity, switches sign here. And then at 2, it switches, becomes positive. And then it goes back, it has to go back to go to the y-axis, to go to the x-axis, because that's the horizontal asymptote. So there's a local max here, local min here. There's no local max or min anywhere on that part. And that's all you can do. So that would give you pretty much full credit. You've covered all the bases here. You've covered all the parts that it asked for. Okay, so that's the 3 questions from that quiz. I'll give you more practice by giving you a mastery assignment, hopefully soon. And you were asked to graph, you were asked to finally graph this, which is what I've done here. Or the class was at that time. Okay. So for now then, I would like to continue now in chapter 6. Exponentials and logarithms. If you have any more questions on this, I can always go back and review it or cover the material. So, exponentials and logarithms. Okay, so in the past we had functions which looked like this. You had x raised to the power of some integer, usually positive or negative it could be. So we had power law behavior. One example would have been this. Or x to the 4th, or x itself, x squared, and so on. So in all these cases, we're taking our x, which we can vary, and we're raising that to a fixed power. Okay, so in our case that we're considering now, we're looking at functions in which you interchange the role of the constant and the variable, and so let's say you fix this part here. This is called the base, and you vary the exponent. The exponent becomes x, the variable here. So all I'm doing then is interchanging the role of the base and the exponent, and these give me completely different functions. Actually, this one here is actually x to the 1. If I interchange the role there, I get 1 to the power x, and we'll see that that's identically equal to 1. Okay, so there's some cases where the exponential function just reduces to something we've seen before, namely the constant function. But there's really only one case where that happens, and and we'll actually not consider those functions. We'll exclude them from our list of useful exponential functions. Okay, so the general case is b to the power x. Okay, so the b is called the base. And the base is usually taken to be, the base will be positive. And not equal to 1. So that means either b is between 0 and 1, not including either end, or b is greater than 1, strictly. So in other words, b is greater than 1, and b is greater than 0, and b is not equal to 1. Okay, so these are the allowed values for the real number, which is the base. Otherwise, it can be any real number. Okay, so yeah, that suggests various questions here. How can you do this without a calculator? How can you calculate such a function at a particular value? X can be any real number, and the base can actually also be any real number. We'll consider actually easier bases. In fact, one of the bases we'll consider, some of them that we will consider will be the base 2 or base 10. Those are simple whole numbers. But another one that's not a simple whole number is e, the natural exponent, which is about 2 point, hopefully I get this right, actually it's 27, I think, 271828, something like that. E is called Euler's number. It's got a special property that we'll deal with, but it's not roughly around. It's close to 3, just a little under 3. Okay, it's probably silly for a mathematician to just guess this number. I should really check this. Yeah, so the way to check it, what I did was I Googled E, and it gave me the number right away. So you can tell the internet was invented by mathematicians, or at least, well, computer scientists, I guess, are mathematicians. Or physicists. Physicists actually invented the internet, and they know all about E. They use it all the time. Okay, so yeah, it's 2.71828. Actually, the next few digits are 1828, but it doesn't repeat, so it's not actually a rational number. Euler is spelled E-U-L-E-R. Euler, that's German. Okay, and so that's going to be an important base to use here. Okay, so now let's just see what these functions typically look like. All right, so to do that, we'll graph a typical one. So let's take the easiest one, which is f of x is equal to 2 to the power x. Here the base is b is equal to 2. It's greater than 1. You could also consider the function 1 over 2 to the power x. Okay, so now in dealing with exponential functions, you'll need to remember your rules for combining exponential operations. If you raise a product like this, or a quotient by a power, then it's the same as raising both numerator and denominator by the same power. So this is 1 to the power x is always equal to 1. So 1 times itself any number of times is equal to 1, just like I wrote over here, and this will be remain 2 to the power x. So replacing b by 1 over b as a base will simply give you the reciprocal function from what you had before. So I've just taken this original function and taken 1 divided by that function, and that's the new function. Okay, so what do the graphs of these two functions look like? Let's call this something different, g. Okay, so that's considering two bases, which are, one is in this range and the other is in this range. Okay, so here's a graph, y equals, x equals y. There's a graph of the x and y axes here. And at x equals 0, remember that any base raised to the 0 power is just 1. So that's true for any base. So here's 1, and the graph goes through that point. If I take x equals 1, so writing a table may be helpful for this first graph. So at x equals 0, I get 1. X equals 1, I get 2. Right? 2 to the raised to the power 1 is 2. And for x equals 2, you have 2 times 2 is 4. X equals 3, 2 times, I get 2 to the power 3, which is 2 times itself 3 times, which is 8. And so on. So you can see this function is going to get big rather quickly. If I put everything in a good scale here, let's try this. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's just write in the even numbers there to avoid congestion of numbers. Okay, so it goes through this point 0, 1. And at 1 I get value 2, so that's right here. 2 I get, this is 1, 2, 3, and so on. 2 I get 4. 3 I get 8. Okay, so it's increasing like this on this side. On the other side, for negative values of x, I get exponents which are negative can be rewritten as in terms of positive exponents by putting that number in the denominator with the absolute value of that exponent. So I just take the reciprocal to get the value of a base raised to a negative exponent. I take simply the base raised to the negative of that exponent. So in other words, strip away the negative sign, take the absolute value. I take the base raised to that positive value, and then I take 1 over that result. So here I get, it's just the same as 1 over 2. And if I plug in minus 2, I get 1 over 4. If I plug in minus 3, I get 1 over 8. So I just take the reciprocals of these values. Okay, so you can visualize that. It might be too small to see in this graph, but here's a half, and that's the value there. If I keep on going further, I take half of that, and that's a quarter, so it'll be right there. And then half of that will be 1/8, so it'll be somewhere there. So it's half the distance from 1 down to the x-axis, Here's 1. Go down to here. And then you take half the distance again from that value of y equals 2, y equals 1/2 to the x-axis, and then that's where the point is, and then you take half the distance again, that's where the y value is. Okay, so connecting all the points, you get this kind of graph. All right. Now, for any base, the graph follows roughly the same pattern here. Oh, okay. Let's look at what happens for g of x. So this is f of x. For g of x, what happens is I have to take the reciprocals of all the values of f of x. So g of x here, you take the reciprocals of all these values, and so this is 1. So this is the same as before. At x equals 0, I still get 1 here. This becomes 1/2 reciprocal. This is 1/4, 1/4. This is 1/8, and this, when I take the reciprocals of these, I get back to 4 and 8. So what that's showing me is that the g of x is simply the reflection of f of x about what? The y-axis. Okay, so I'm trying to draw it carefully here. I get 2 there instead of 1/2. I get 4 here. Oops. And here I get 8. And here I get, going the other way, 1/2, 1/4, 3. So this one goes down like this. Never touches, neither curve ever touches the x-axis, but it gets closer and closer. In fact, extremely close. Very quickly, as x, in this case, as x goes to infinity for g, and as x goes to minus infinity for f of x. Okay, so g of x is the reflection of f of x about the y-axis. Okay, otherwise, actually, by themselves, neither f of x or nor g of x have any symmetry. There's no vertical symmetry or odd symmetry or even symmetry in either of them. But it's interesting that just changing the base by replacing b by 1/b does result in this reflection about the y-axis. Now, what happens for other b? What other values of b? Okay, well, for any value of b, the value of the exponential function at, so let's try b, h of x is b to the power x. The value at x equals 0 is still 1, right? Let's take another b different from 2, something though that is still bigger than 1. Okay, so the value, just looking at what our table would look like. So this is true for any b. So I'll write things in terms of b here. So if x is 0, then again h is 1. So the graph still goes through this point 1, 0. All the exponential functions, which are simple like this, go through that point. If I take x equals 1, I get the value simply b. So whatever the base is, I can see what it is by going to the point x equals 1, and that will identify what the base is. So let's say this base is e. So this would be about here, 2.71, 2.72. Okay, and if I take 2, then I'll get b squared, which will be up here somewhere 9 or 8 something. Okay. On the other side, I'll go 1 over e. Minus 1 is 1 over e, 1 over b here. And minus 2 will be 1 over b squared. So here it's going faster towards 0 than in the previous function 2 to the power x is going to 0 when x goes to minus infinity. And here it's going off, increasing even faster than 2 to the power x. So the bigger the base, the faster it increases to infinity in the positive x direction, and the faster it decreases to 0 in the negative x direction. If I replace b by 1 over b, then I'll get similar behavior. It's just reflected. I just get what I did before was I just reflected in the y-axis, and here I'll get this same behavior. So this is base b. Actually, base e is what I'm choosing here. And this is going to be 1 over e. So at x equals minus 1, I get about, again, 3. Identify all the bases here. Okay. Now, in all these cases, what I have in common is that there are no horizontal asymptotes. But I do get a vertical asymptote in one direction. Sorry, the other way around. One horizontal asymptote, namely y equals 0, and no vertical asymptotes. Okay, so this function is increasing off to infinity, but there's no boundary line which it approaches closer and closer to. Because x can be anything. X will extend all the way in this direction. So for each value of x, the function will be way above it somewhere. There over here, if you just go a little further away, that function will be very, very far out. But it will still be all the way, there will still be a value above that point x. All the way as x goes to infinity. Okay, so there are no vertical asymptotes here. Only the one horizontal asymptote. And it's only reached for one in one direction. Either x goes to plus or minus infinity, or x goes to minus infinity, not both directions at the same time. This is approached for x goes to plus infinity, or x goes to minus infinity, not both. Now, I want to also introduce logarithms. We've done exponentials a little bit. I want to introduce the idea of an exponential, or the logarithm function. Okay, let's just see where we are here. Oh. Did I get signed off? Okay, so I'm still live streaming here. So let's see what the logarithm function is. Okay, basically the logarithm function is essentially the inverse of the exponential functions. And remember, the property of an inverse function is that if one function is an inverse of another function, then the original function is the function of it is the inverse of its inverse. So these go both ways. Exponential and logarithms are inverses of each other. So the way we write that is y is equal to the log base b of x. This means all right. So I first verify. I look at these functions, and I verify that no matter which one I'm going here, if it's a base that's less than 1, greater than 0, or a base that's greater than 1, both are one-to-one functions. Okay. They're one-to-one on the entire domain. Domain for the exponential function by the way, it's often written as in this way, xb of x. Sometimes it's written like that on a calculator. Actually, the exponential function on the calculator is just b is equal to e. Usually, although you have e to the x on the calculator, so that's where the base is equal to e, and you also have 10x on the calculator. Okay, and you can actually construct on a graphing calculator any base to the power. You just raise 2 to the power whatever you want, and you can get a function. You can call it x even, and then you can create whatever exponential function you like on a graphing calculator. So the domain of an exponential function, x can be positive or negative or 0, doesn't matter. You get values for all, let's say, the integers, ones you can easily calculate, and by approximation, all the any rational number you'll be able to get you'll be able to evaluate that that value. By the way, I didn't say much about that, but so if r is a rational number, if it's an integer, then you just take powers of that b. And if they're positive, you just leave it as it is. If they're negative integers, you take the absolute value of b to the absolute value of that power, and then take 1 over that b. So for integers, it's easy to evaluate this expression. If r is rational, you can still evaluate it, because r will be of this form, p over q. P is an integer, and q is a positive integer. It can't be equal to 0, right? And let's say this is of lowest form. So by the way, that's what you saw that in the homework. There was a GCD. That means greatest common divisor of p and q is 1. So that means there are no factors common to them. They've been canceled. Or they're also called, it's also called p and q are relatively prime. They may not be prime by themselves, but neither of them might be prime by itself, but they have no common factors, and that means that's another way of saying that they're relatively prime. Okay, so given a rational r, what you do is to get the value of y here, you first raise b to the power p, and then you take the qth root of that. Oh, and if p is an integer, it could be negative, so you should take the absolute value of that, p. And then, depending on whether the original q you can take to be positive integer. I'll indicate it like that. These mean contained in. The epsilon looking figure here, or symbol there, that means contained in. So we say p is contained in the z, which is the original of the integers, and q is contained in the positive integers. Okay, and this would be the result if p is positive, or qth root of this and 1 over. So in the end, I raise everything to the -1 if p is negative. Okay, so these operations can be, this calculation can be done for any rational number with given p and q. And what happens is you can always approximate any real number by a sequence of rational numbers. You can get closer and closer to that rational number by choosing, p and q appropriately. Okay, so with the result you get by doing these operations, then that will give you a number which approaches the number b of x. If r approaches x, then this approaches b of x. Okay, so any value, you can find this expression for any value of x that you like, any real value, just by approximating that real value x by some rational number, and then you raise b to that rational number. And those operations you know how to do. Okay, so anyway, I think that's probably enough for today. I'll discuss logarithms next time. But basically, that's what we're going to do next. Logarithm functions are simply the inverse functions of the exponential functions. Okay, so that's all for today. I hope you have a good day, and I hope doing the homework's going well. If you have any more questions on that, please let me know by email or chat. And so take care and have a good day. Hudofes.